All right, guys, we're going to work on 6.3 today, vectors in the plane. This may take a little while. If it takes the whole period, then you guys will just have your work tomorrow, and then we'll do 6.4 on Wednesday. I'm not real sure how long it's going to take, but as soon as I finish recording, I'll know, and I'll set up your Canvas stuff so that you'll be able to see exactly what you should do. So 6.3 vectors in the plane. So quantities such as force and velocity involve both magnitude and direction. And cannot be completely characterized by a single real number. To represent such a quantity, you can use a directed line segment as shown below, and I'll show you guys that in just a minute. The directed line segment PQ, and it has this little symbol above it. So it looks like this, PQ, and like a half arrow. Has an initial point P and terminal point Q. Its magnitude or length is denoted by, it's almost like absolute value bars, but double ones. PQ with that little symbol, and can be found using the distance formula. So you're going to have a line segment. This will be P, or your initial point. And then you'll have point Q, which is your terminal point. And this line is called PQ, and like I said, with the symbol on the top, so a directed line segment. I'm going to draw a little helping line for myself so I can show you the next things that we have. So we're going to draw a few of these little lines. They're going to come from there. And then we're going to draw a couple more down here on this one. And again, these are just helping lines. So they don't really exist in the figure. They just helped me draw them a little bit nicer and evenly. So two directed line segments that have the same magnitude and direction. Are equivalent. The set of all directed line segments that are equivalent to the directed line segment PQ is a vector V in the plane written V equals PQ. Give you a minute just in case you were still drawing those lines. And that last little sentence just said that vectors are denoted by lowercase boldface letters. And you guys will see like especially in the example that you're seeing at the bottom, you can see that U and V are bold. It's really hard to do that with my pencil, so I try to just go over it a couple times. So you'll see that throughout these notes. If you don't want to make them bold, you don't have to. I just like to do whatever the book says. All right. So it says show that U and V are equivalent. And remember, it said you could do that using the distance formula. So we're going to start with PQ. Just to remind you, the distance formula is x minus x squared plus y minus y squared. And I always do it left to right. You might have seen it as x2 minus x1 plus y2 minus y1, which you would go backwards. It doesn't matter as long as you keep them consistent. So if you start with R and finish with S, when you go to your Y's, start with R, finish with S. Same thing, P to Q, then finish with P to Q. So my X's for P is 0, minus Q is 3. Do the same thing for Y. For P is 0, minus Q is 2. You guys are going to put that into your calculator. I know that you will, but we're just going to do it together. 0 minus 3 is 3, squared is 9. 0 minus 2 is negative 2, but when we square it, it becomes positive, which is 4, which gives us the square root of 13. You do not have to simplify this. There's nothing you can do to simplify it. If you can, you probably want to. Once you get RS, if it doesn't look like this and you need to simplify, then go ahead and do that. Okay. So then we're going to do RS. Same formula. Your X for R is 1 and S is 4. So 1 minus 4 squared. Plus, you have 2 and 4. 2 minus 4 squared. 1 minus 4 is 3 or negative 3, but when we square it, it's going to be positive. So it'll be a 9. 2 minus 4 is negative 2 squared is 4. And you can see that these are exactly the same. So again, show that U and V are equivalent since they're both equal to square root 13. They're good. Okay. So that is just for their magnitude. So this part is their magnitude. You can do their slope for the direction. So for your slope of RS, remember your slope is y2 minus y1, or I just do y's. It doesn't matter which one. So let's do PQ first. PQ, your y's are 0 and 2. Your x's are 0 and 3, which gives you a positive 2/3. When we do RS, our y's are 2 and 4. 2 and 4, and our x's are 1 and 4, which gives you 2/3 when you reduce it. So we can see that these two are exactly the same, and this is the direction. So again, magnitude deals with distance, and slope deals with direction. The component form of a vector, the directed line segment whose initial point is the origin. So P up here is a directed line segment whose initial point is the origin. Is often most convenient representative of a set of equivalent directed line segments. This representative of the vector V is in standard position. A vector whose initial point is the origin 0, 0 can be uniquely represented by the coordinates of its terminal point V1, comma V2. This is the component form of a vector V. And then we can write that as V equals, and it's like a less than sign, so it's a new type of bracket that you're seeing. V1 comma V2, and then like a greater than sign. Where the coordinates V1 and V2 are the components of V. If both the initial point and the terminal point lie at the origin, then V is the zero vector and is denoted by 0 equals 0, 0. Just in case you're behind. So again, remember your initial point is where you started, your terminal is where it ends. If we look back at that figure, it started at P and it ends at Q. What this is saying, if it starts at P and ends at P, so that is your initial and your terminal, then it didn't go anywhere. So there's going to be no magnitude and there's going to be no direction. So that's why it's going to be a 0, 0. Okay. The component form of the vector with initial point P that has P1, P2, and terminal point Q, Q1 and Q2 is given by so that the way you denote the directed line segment PQ with that like half the arrow looking thing equals Q1 minus P1 comma Q2 minus P2, which gives you your V vector V1 V2 or just V. The magnitude or length of V is given by, we just talked about that, those two little bars with the V inside. And it's always the distance. So the magnitude is the distance. Q1 minus P1 squared plus Q2 minus P2 squared, which would be the same thing since Q1 minus P1 is V1 and Q2 minus P2 is V2. V1 squared plus V2 squared underneath the square root. Okay, again, remember magnitude deals with the distance, direction deals with the slope. If that magnitude is going to equal 1, then V is a unit vector. Remember, just like the circle, the unit circle is based off of 1 to the left, 1 to the right, 1 up, 1 down. This is the same thing. So anything that's 1 is a unit. So unit vector. But then if it is equal to 0, if and only if V is the 0 vector. So again, that's when it doesn't move anywhere. So we're going to find the component form of a vector, and we're going to do the form and magnitude of the vector that has the initial point 4, -7, and the terminal point -1, 5. So we're going to do exactly like this says. I'm going to pull it back up so you guys can see it at the same time. So PQ, we're going to use this formula right here at the top, is equal to Q1 is your terminal point. So this one is your initial point. So P1, P2. This one is Q1 and Q2. So Q1 minus P1, -1 minus 4. And then Q2 minus P2. 5 minus -7 is going to be 5 plus 7. It's going to give you the vector -1 minus 4 is -5. And 5 plus 7 is 12. So there's the component form. Now I need to find the magnitude. So the magnitude, so again, this is component form. Now I need to find the magnitude, and that's your distance. That's going to be your initial 4 minus -1 or 4 plus 1 squared. I just go in order with this. If you want to find the formula, that's perfectly fine. It's all going to turn out the same. -7 minus 5 squared. But remember, 4 plus 1 is 5. That comes from here. So you could just take this and plug it into the distance formula as your square root of 5 or -5 squared. It doesn't matter because it's going to turn to positive, plus 12 squared. And that is going to be our magnitude. 5 squared is 25. 12 squared is 144, which equals the square root of 169, which ends up being 13. So again, you don't have to write all this out. You can just use your component form. So on the next one, I'll just use the component form, but I again wanted you to know where it came from. So find the component form and magnitude of the vector v that has the initial point -2, 3 and the terminal point -7, 9. So we're going to do PQ again. We're going to do Q1, which is -7, minus P1. So a minus -2 is a +2. Terminal point minus initial point, which gives you -5, 6. Instead of doing all the work to find the magnitude, you can use these two. So -5 squared plus 6 squared. -5 squared is going to be a positive 25. 6 squared is 36, which gives you the square root of 61. You don't have to simplify that. It won't simplify. So that is as good as that one is going to get. Just give you a second to get it, and then we're going to move on. All right. So remember, I told you once I write these, if you see any that I'm like rewriting over and over again, that's your bold face. So there's a couple in here that are going to be bold. The two basic vector operations are scalar multiplication and vector addition. In operations with vectors, numbers are usually referred to as scalars. And you learned about scalars a long time ago, even if you don't realize it. I've taught scalars in Math 1. So again, it's just what you multiply by. In this text, scalars will always be real numbers. Geometrically, the product of a vector v and a scalar k is the vector that is absolute value of k times as long as v. When k is positive, kv has the same directions as V. So then when K is negative, KV has the direction opposite that of V. And again, give you a minute to copy it and we'll flip it. So you can see that all those V's are supposed to be bold. To add two vectors U and V, geometrically, first position them without changing their lengths or directions. Sorry. So that the initial point of the second vector V coincides with the terminal point of the first vector U. The sum of U plus V is the vector formed by joining the initial point of the first vector U with the terminal point of the second vector V. This technique is called the parallelogram law. For vector addition, because the vector U plus V, often called the resultant of vector addition, is the diagonal of a parallelogram having adjacent sides U and V. So the definition of vector addition and scalar multiplication. Let U equal the vector U1, U2, and V equal V1, V2. So we're going to let those be vectors and let K be a scalar. Remember, K in this text is always real numbers. Then the sum of U and V is the vector. So if we add U and V, we're going to do U1 plus V1 and U2 plus V2. And the scalar multiple K times U is the vector KU. So K times U1, U2, which is the same thing as KU1, KU2. So there's your rules for sums and scalar multiplication. The negative of vector v, which was v1, v1, v2, is negative v, which is the same thing as negative 1 times v, which is negative v1, negative v2. And the difference of u and v is u minus v equals u plus negative v. Remember, we just changed it to plus negative. And it will be the same thing as u1 minus v1, comma, u2 minus v2. To represent u minus v geometrically, you can use directed line segments with the same initial point. The difference u minus v is the vector from the terminal point of v to the terminal point of u, which is equal to u plus negative v. So it looks like a lot, but vector operations are exactly like any other operations. So if we're adding coordinates, x's plus x's and y's plus y's or minuses, and so on and so forth. If you're multiplying, make sure you multiply to everything. Vector operations, let v equal negative 2, 5, and w equal 3, 4. Find each of the following vectors. All this space is not needed, so it looks like we're going to do a lot of work. We're really not. So we're going to do 2 times v, which is going to be 2 times negative 2 comma 5. It's just like any other problem with multiplication. You're going to distribute it in. So we're going to do negative 2 times 2 and 5 times 2, which is negative 4, 10. There is no more work to that. That's it. Okay, so don't stress out. It literally is just multiplying it throughout. So w minus v, make sure you put it in the right order. So w was 3, 4 minus v is negative 2, 5. So you're going to subtract them. Subtract your x's, subtract your y's. So 3 minus negative 2, 4 minus 5, which gives you 3 plus 2 is 5, and 4 minus 5 is negative 1. Same thing on the next one. If you were doing order of operations, you would do that 2 first. So that's what we're going to do. We're going to start with our v, which is negative 2, 5. Oh, sorry, that should be. And then 2 times your w is 3 plus 4. So we would do negative 2, 5. Order of operations says multiply first. So when I distribute that in, that should not be a plus, that should be a comma. When I distribute that in, I get 6, 8. And then you just add them like normal. So negative 2 plus 6 and 5 plus 8, which gives you 4 and 13. So again, follow order of operations just like normal. So we're going to do it again at the bottom. We have U and V. U is 1, 4, and V is 3, 2. Find each of the following vectors. So U plus V. So we're going to do 1, 4 plus 3, 2. And again, you just add them up. So 1 plus 3, your x's, and then 4 plus 2 for your y's. And we get 4, 6. You do not have to show all of that work if you do not want to. Okay, you can do it in your head. That's perfectly fine. I'm just going to show it on your notes just so you have something to reference back to. U minus V. U is 1, 4 minus V is 3, 2. So we're going to do 1 minus 3 and 4 minus 2. 1 minus 3 is negative 2. 4 minus 2 is 2. And then last 2U minus 3V. And we're going to distribute in and then we'll subtract. So 2 times U, which is 1, 4, minus 3 times V, which is 3, 2. We're going to distribute in. I'm not going to distribute the minus. I'm going to leave it alone for right now. So I get 2 8 minus 9, 6. Then I'm going to do my 2 minus 9 and 8 minus 6. 2 minus 9 is negative 7. 8 minus 6 is 2. Sorry, that looks like 27, but that's my little vector symbol. All right. So then down at the bottom, you have properties of vector addition and scalar multiplication. You've pretty much done all of those, and you guys can see that there are properties here where you have to add U and V, and then you add W, so on and so forth. Obviously, we add a positive and a negative, we're going to get 0. This is distribution. This is just the order that they're put in. Remember, when we multiply, we can multiply in any order that we want to. And then you can take this C out when you're working with the vector. Here is your unit vector and your 0 vector. All right, next page. In many applications of vectors, it is useful to find a unit vector that has the same direction as a given non-zero vector V. To do this, you can divide V by its magnitude to obtain. We said U was the unit vector. And we could find the unit vector by taking V and dividing it by its magnitude. And then we can split up fractions, remember, just like this. Note that U is a scalar multiple of V. The vector U has a magnitude of 1 because it's a unit vector, and the same direction as V. Direction, remember, is slope. The vector U is called a unit vector in the direction of V. So again, all we're doing is trying to find the unit vector. So find a unit vector in the direction of V. of 6, -1, and verify that the result has a magnitude of 1. So to find the unit vector, we divide by the magnitude. So V is 6, -1. That means our magnitude is 6 squared plus -1 squared underneath the radical. When we simplify this, 6 squared is 36, -1 squared is 1, which makes 37. So this corresponds with this part. So now we're going to pull out the denominator and multiply it by the numerator. So we're going to have 1 over the square root of 37. And then we're going to multiply that by 6, -1. You don't have to show this step. Technically, what you're going to do is put your 6 and your -1 over that same denominator. So you split it up. So you get 6 over square root 37 and -1 over the square root of 37. So that is your unit vector. It said verify that the results has a magnitude of 1. So we're going to check that magnitude. And remember, magnitude is the same thing as the distance formula, but we're going to check this magnitude. So we're going to do 6 over the square root of 37 squared plus -1 over the square root of 37 squared. When you square them, you square the top and the bottom. So 6 squared is 36. Anything with a square root, a square will cancel out. So it's 36 over 37. When we square -1, we get +1. When we square the square root of 37, we get 37. When you add these fractions up, 36 plus 1 is 37 over 37. 37 over 37 is 1. And the square root of 1 is 1. You're going to do the same thing on the next one. Find a unit vector in the direction of V, -2, 5, and verify that the result has a magnitude of 1. So we're going to do the same exact thing. So we're going to take V over the magnitude of V. So -2, 5 over the square root of -2 squared plus 5 squared. That will simplify down to 4 plus 25 is the square root of 29. And remember, I told you can skip this step where you pull them apart. And you can just write it as -2 over the square root of 29 and 5 over the square root of 29. So that is your unit vector. And then we were going to test our magnitude. Sorry, guys. Which again is that distance formula. So we're going to have -2 over the square root of 29 squared plus 5 over the square root of 29 squared. -2 squared is 4, and we're going to take off the square root of 29. 5 squared is 25 over 29. 25 plus 4 is 29 over 29, or the square root of 1, which is 1. The unit vectors 1, 0, and 0, 1 are called the standard unit vectors. And are denoted by a regular font. I know that we have imaginaries where we have like a little, like this curly I means imaginary. This is a regular font, just to know the difference between the two. That is your 1, 0. And again, it's a vector, so it's bold for you guys. And then J is your 0, 1. These vectors can be used to represent any vector V of V1, V2 as follows. So if we have vector V, that is V1, V2. Then our V1 can be multiplied by 1, 0, again, because it's a unit vector, so multiplying by 1 does absolutely nothing, plus V2 is the one with the X, is because V1 is the X coordinate, so that's why our 0 is Y. And then over here, V2 is your Y coordinate, so the 1 has to be with the Y coordinate. And when we multiply that out, that gives us V1I plus V2J. The scalars V1 and V2 are called the horizontal and vertical components of V respectively. Again, horizontal goes with the x-axis or the x coordinate, and vertical goes with the y-axis or the y coordinate. The vector sum V1I plus V2J is called a linear combination. They're going to be a linear combination of the vectors I and J. Any vector in the plane can be written as a linear combination of the standard vectors I and J. So we're going to take these vectors and write them as linear combinations. So it says, let U be the vector with initial point 2, -5 and terminal point -1, 3. Write U as a linear combination of the standard unit vectors I and J. So we're going to go back to the beginning where we got to put these together. So remember, it's terminal minus initial. So our terminal is -1 minus initial 2. Terminal 3 minus initial -5 is going to be +5. We're going to add those up or subtract them. So -1 minus 2 is -3. 3 plus 5 is 8. And then as a unit vector, you're just going to put the -3 with I plus 8J. And again, everything can be written like that. So your X coordinate goes with I and your Y goes with J. So we're going to do this again. Let U be the vector with initial point and terminal point. So again, terminal minus initial. Our terminal was -8 minus -2 would be a +2. and then 3 minus 6. When we put those together, negative 8 plus 2 is negative 6. 3 minus 6 is negative 3. And then to write it as a standard unit vector, you're going to have your negative 6 with I plus your negative 3 with J. You can also write it, sorry, not a curly I, as negative 6I minus 3J. Again, I don't care which way you give it to me. It's up to you what you want to do, whatever you like better. Two more on this page. Let U equal negative 3I plus 8J, which is what we got up here. And V equal 2I minus J. Find 2U minus 3V. It's the same thing. So we're going to multiply the U and we're going to multiply the other one. So U is negative 3I plus 8J. We're going to take that and multiply it. And then we're going to subtract 3 times V. And we're going to distribute throughout. So we get negative 6I. Again, not curly. I shouldn't write it like that. Negative 6I plus 16J. Distribute negative 3 to make negative 6I plus 3J. And then add your like terms. So negative 6I minus 6I is negative 12I. And then 16J plus 3J is 19J. Again, these are all easy things to do. Just treat it like normal I and J or like X's and Y's. Okay. Let U equal I minus 2J. V is negative 3I plus 2J. Find 5U minus 2V. So 5U minus 2V. Distribute, you get 5I minus 10J. Negative 2 times negative 3 is a positive 6I. Negative 2 times 2 is negative 4J. Add your like terms. 5I plus 6I is 11I. And then negative 10 minus 4 is negative 14J. Couple more pages, we're done. I'm sorry it's taken a long time. If U is a unit vector such that theta is the angle measured counterclockwise from the positive x-axis to U, then the terminal point of U lies on the unit circle. And you have that U is equal to xy. Remember, your x coordinate is cosine of theta. Your y coordinate on your unit circle is your sine of theta. And to write it as a unit vector, we would do cosine theta I plus sine theta J. The angle theta is the direction angle of the vector U. So I'll give you a minute to catch up. So again, if you relate it back to the unit circle, x is your cosine, y is your sine, and then we can write it as the unit vector by putting the I and J in. Suppose that U is a unit vector with direction angle theta. If V is equal to AI plus B times J is any vector that makes angle theta with the positive x-axis. Then it has the same direction as U. And you can write B is equal to the magnitude of V times cosine theta sine theta. So then we would have the magnitude of cosine theta I plus the magnitude of sine theta J. Because V equals AI plus B times J, and it's the same thing as the magnitude of V times cosine theta I plus sine theta J. It follows that the direction angle theta for V is determined from tan theta being equal to sine over cosine so the magnitude times sine theta over the magnitude times cosine theta is actually going to give you from right here B over A. So again, sine theta is the same thing as cosine, sorry, as the y coordinate of your point on your unit circle, and cosine is the x coordinate. And remember, we know that tan is y over x. So it's going to be the same thing as B over A because this is your xi plus your yj, so y over x. So all of this is just kind of proving it, but you already knew tan was y over x, and that this is like your x coordinate and this is like your y coordinate. So we can change it instead of x and y into A and B. So B over A. The next example is say find the direction angle of each vector. So if we look, your coordinate is 3, 3, and that comes from these two numbers, your x coordinate 3, your x coordinate, or your y coordinate 3. And this is in quadrant 1. The reason that is important is because when you finish, what should you have? So our tan theta is going to be B over A or y over x, whichever one you want to do. In this case, they're both the same, which gives you 1. And then we have to figure out that equation. So we want to know the direction angle. So tan theta equals 1. Grab my calculator real fast. I have to do it on my phone, so I apologize. Get it pulled up. We're trying to put it in degrees. So we're trying to find the angle to make sure it's in degree mode. And then to get theta, remember theta equals tan inverse of 1. So second tan 1. And we get that our angle theta is 45 degrees. We're going to do the same thing on the next one. Your coordinate is going to be 3, -4. But 3, -4 is in quadrant 4. Okay, so again, if I do my quadrants out, just in case you keep forgetting, we would go over 3 and down 4, which will be in quadrant 4. We're going to do that tan theta is y over x. And then we need to find theta by doing tan inverse of -4/3. Pop that on my calculator. Tan inverse of -4/3 gives us -53.13. Now, if we're in, sorry about that, guys. If we're in degree mode here and we're going -53, we're trying to get to quadrant 4. Remember that this is 0 or 360. Now we're going to go backwards, 53.13. So I'm going to take that 360 and subtract 53.13. And that's going to give me my actual angle, 306.87. So that would be your final answer. And again, because we have to have an angle in quadrant 4. We're going to do it again. We'll go ahead and put this up here one more time. 1, 2. You don't have to write it down. I just want it to be seen on the screen while I'm doing the next step. Your coordinate is -6, 6. If I graph that, I'm going to go to the left and up. So that puts me in quadrant 2. We're going to do tan theta equals y over x. So we get tan theta equals -1. I'm going to do tan inverse of -1, and I'm going to get -45. If we're in quadrant 2, this is 180, and I'm going backwards 45. I'm going to do 180 minus 45. So again, quadrant 2, what that's helping you do is get this angle right here that you're subtracting from. In here, we were in quadrant 4, so we used 360. Okay, 180 minus 45 is going to be 135. The worst five I've ever drawn in my life. Sorry, guys. All right. Oh gosh, that didn't get much better. I think there's something under my paper. There we go. All right, 135. The last one, we have the coordinate -7, -4. So if we go -7, -4, we're going to be in quadrant 3. We're going to set this up. Tan theta equals -4 over -7. Use your calculator to find that, and you can keep it just like it is. Tan inverse -4 over -7. You don't have to simplify it if you don't want to. Gives you that theta equals 29.74. So if we're in quadrant 3 and I go back here, we're talking about 180, and we have a positive 29, so we're going positive this way. So we're going to do 180 plus 29.74, which is going to give us 209.74. All right. So again, use those quadrants. You have your cheat sheets, use those. They'll probably help you out a little bit. Okay. Getting close, guys, almost done. Applications, finding the component form of a vector. Find the component form of the vector that represents the velocity of an airplane descending at a speed of 150 miles per hour at an angle 20 degrees below the horizontal as shown below. All right. So on this one, We're going to talk about the distance formula in a minute, but I'm going to go ahead and tell you distance formula is not going to be needed. Because remember when we're trying to solve a triangle, that distance formula tells us our hypotenuse. And we already know that our hypotenuse is 150. We'll come back to that though, okay? So here's what we have. V equals, find the component form of the vector. The magnitude of V times cosine theta I plus the magnitude of V times sine theta J. Here's where that magnitude comes in. You can do it, but why when they're already right there for you? So this is our magnitude, 150. It says it's at an angle 20 below. So this horizontal line, your x-axis is 180 plus 20 is going to give you this 200. So that's where this 200 is going to come from. So we're going to do cosine of 200 times I plus 150 sine 200J when you put that in your calculator, figure all this out, 150 cosine 200 gives you negative 140.95. And then we have that I, 150 sine 200 gives you negative 51.30. And we have the J. So then your component vector is going to be those two numbers, negative 140.95 and negative 51.30. That's it. Okay. Looked like it was going to be hard, but it's not too bad. I'm going to read this one while you guys are still writing that if you still have it. A force of 600 pounds is required to pull a boat and trailer up a ramp inclined at 15 degrees. From the horizontal, find the combined weight of the boat and trailer. All right, so I'm going to give you some information. The magnitude of BA, so you guys see B and A, equals the force of gravity which equals the combined weight of boat and trailer. BC, so this is BC, is the force against the ramp. And AC, here's your AC at the bottom, is the force that is required to move the boat. Up the ramp. And from the problem, they told us that that was the 600. A force of 600 pounds is required to pull the boat and trailer up the ramp. All right. So if we look at, I'm going to pull this out, B, A, C, it gave us 15 degrees. We have side BC and BA. So we can set that up as sine 15 degrees. Let me make my picture a little better so you guys can see it. If you can see it in the photo, you can see the right angle down there. So I'm gonna change it up just a little bit and kind of put it straight up and down. So B, C, and A, they gave us 15 degrees. So this would be your opposite, this one would be your adjacent, and this is your hypotenuse. So why are we using sine? Because we're going to use AC and BA because these are the two that we have right here. So opposite is AC, hypotenuse is BA, and it doesn't matter which order you write them in. If you write it AB, it would be fine as well. We know that AC is 600. And again, we're looking for the combined weight of the boat and trailer. So that's what we're looking for. That's why we used BA and we knew AC. Cheater method tells you to switch these two so that you can solve. Sorry, not that. BA is going to go up here. And it's going to be 600 over sine 15 degrees. Since it's 15 degrees, we're going to put it in degree mode. I'm going to make sure that that's what I'm still in. And we're going to do 600 over sine 15. And we're going to get 2318.22. And that's your final answer. That's it. Okay. Last one, and it's a fairly lengthy problem, but pretty simple. So again, last one. Yay. Using vectors to find speed and direction, an airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees at a fixed altitude with a negligible wind velocity as shown in figure A. So this is it right here. When the airplane reaches a certain point, it encounters a wind with a velocity of 70 miles per hour in the direction north 45 degrees east as shown in figure B. What are the resultant speed and direction of the airplane? So we're going to start with the very first one, the velocity or the V of the airplane. So this is airplane velocity. This one, when we do it in a second, will be the wind velocity. The airplane is traveling at a speed of 500 miles an hour. We're going to multiply that by cosine of the angle. The angle is 120. Sine 120. Why are we doing that? Because we're finding that coordinate. Remember the coordinate x is cosine and y is sine. So again, it just deals with the x and y coordinate. If we look at this, cosine 120 is going to be a negative 0.5 times 500 is negative 250. Do the same thing for the other one. You can do it all together if you'd like. And it'll give you some weird number. Now, this weird number, you can use the decimal if you want to, or we can use our cheat sheet. We can use our cheat sheet for sine 120. And when we multiply it by 500, we're going to get 250 times the square root of 3, because sine 120 is square root of 3 over 2. So this is square root of 3 over 2. And when we multiply it by 500, that reduces to 250 times square root of 3. For wind velocity, it said it has a 70 mile per hour And it said that theta was in the direction north 45 degrees east. So 45 degrees from north. And we get cosine 45 sine 45. So we started at north and went east 45, and that's going to still just give us 45 because that's directly in the middle. Cosine of 45 is square root of 2 over 2, and sine of 45 is square root of 2 over 2. So 70 divided by 2 is 35 square root of 2, and 35 square root of 2. These are going to both be the same. So it said what are the resultant speed and direction of the airplane, so we've got to put those together. So the direction, speed, and direction of the airplane. So when we put D1 and D2, the airplane and the wind together, we're just going to add them up. So we have negative 250 plus 35 square root 2, 250 square root 3, plus 35 square root 2. And again, I'm just putting those together, adding those. And we're going to go ahead and do some decimals here. So when I put it in my calculator, and I'm going to go ahead and give them to you, but we're going to add these in our calculator. We get negative 200.5 and 482.5. And I told you up here, it wouldn't have mattered if you would have gave me a decimal. So you don't have to use a cheat sheet. You can use decimals because it's going to come out to be a decimal anyway. No worries. So then the speed of the airplane is going to be your magnitude. So that's your distance formula, negative 200.5 squared plus 482.5 squared is going to give you approximately 522.5 miles per hour. So your speed or your magnitude, 522.5. And then it asks for the direction. So remember your direction is like your slope. So that would be your tangent. And in this case, the direction has to be a degree. So that's why I use tangent. And remember your slope is y minus y over x minus x. Tangent is y over x. So remember this is b over a, or even like I said, y over x, which is going to be that 482.5 over negative 200.5, which gives you negative 2.4065. So tan theta equals negative 2.04065. To find theta, you're going to do tan inverse. Sorry, you can't even see it. You're going to do tan inverse of that number. And you get negative 67.4. So again, we're up here in this quadrant with that airplane if you guys look at all your other things. So we're going backwards 67.4. So theta is going to equal 180 minus 67.4, which is 112.6. However, your true direction is going to be 270 plus 180 minus 112.6. And again, that's to get a coterminal angle because we had a bearing of 330. Again, because we had a bearing of 330. So we're gonna do the 270 plus 180 minus 112.6, which gives us 337.4. And again, this just has to do with that bearing of 330 degrees. Okay. All right, so that's all of 6.3. If you'll look on Canvas, I'll check the recording and see how long it is. And then if this is taking up the whole period, then you will do your homework tomorrow. If not, then you'll see your homework assigned in Canvas for you. All right, y'all have a good day.